questions. And 4 papers that I've submitted for my class. We've sent 3 emails because my book isn't working. No response from those people. Paying so much money for this course, and they won't give me response.
You're at Southwest?
Yeah, here in Southwest, where SU makes you happy.
That sounded very forced.
All right, so the scan converter. What do you think the scan converter is?
And the information to image.
Yeah, that's pretty much it. Okay, so the scan converter converts the information that the machine gets from the transducer into a way that it's displayable on the machine. Okay, because if we just got the information from the transducer and put it right onto the screen, it would just be a bunch of different numbers. Okay, so the scan converter converts information from the transducer, converts it into information that is displayable on the screen. Okay, so the scan converter first stores information from the ultrasound machine and then converts it. Okay, so it doesn't happen instantaneously. Okay, the machine needs some time to process the information. So before it loses it, it stores it. Okay, it stores it, breaks it down, and then sends it to the display. Okay, everybody get that? Okay, so storage of image information is called writing. Okay, so we write something down, we're storing it. Now, later the image data is read from the scan converter for display on the monitor. Okay, so we can say that real time is writing, and accessing that stored information is called reading. Okay, so right now you guys are writing in your notebook. Okay, but then later on, you're gonna go over it and you're gonna read it, right? Okay, so we could say that writing is real time, reading is post. Okay? Ultrasound information is obtained from pulses emitted by a transducer that penetrate the body in a spoke format. By spoke, what are we talking about? Like the past tense of speak? Or spokes on a wheel, maybe?
Past tense.
No. No, we're talking about the spokes of a wheel, okay? Does everybody know what a spoke is? No? On a bicycle tire, those thin metal rods are called spokes, okay? So the spokes travel outward the same way it travels like a transducer. Okay, so the transducer sends out the information in spokes, okay? And what are these spokes called? We went through it already. What's that lines? Scan lines, okay? Each of these is a scan line, okay? And each scan line has what?
Information.
Its own information, okay? And what is sent through these scan lines?
The data?
Starts with a P, pulses,
Oh.
okay? So there's pulses sent through each scan line. And what is received in each scan line?
Echoes.
Echoes, yes, very good. Okay, so each of the scan lines has its own information that it, okay, so it is sent, the pulse is sent into the body, then it is echoed back, right? Okay, it is stored by what? The scan converter, and then what's happened, and then what happens to the information that's in the scan converter? It's read or it's converted into information that is displayable, right? Okay, that makes it image. Okay, so the scan converter translates the information from spoke format into video format. Okay, so from the format that looks like this into a video format where it makes an ultrasound image on the screen. Okay, in the earlier days of 2D imaging, we used analog scan converters. Yes.
on the, picture,
Uh-huh.
it shows how like it works right from the transistor to the pulsar receiver.
Yeah,
But it also has a pulsar straight to the scan converter.
yeah.
How's that, is that like, could you explain that?
Okay, so when we're sending out the pulse, okay, so it's not the pulsar straight to the scan converter, it's the information.
Oh.
Okay, it's the information from the pulsar, so, how are the echoes placed on the screen? What's used? What's
Voltage?
calculated?
Voltage?
No, what's calculated to assign that dot to that certain pixel on the screen?
Hands.
What?
Where's the hands? Where's the hands?
Come on, you guys, it's like the elemental thing.
Okay, say the question.
How do we determine where that dot is placed on the screen?
Oh.
What's used?
The crystal?
No, not the crystal. Time and depth. Time and depth. Okay, so how do we know what time that pulse was sent?
Because where it came from?
Okay, so it's good, so that information from the pulsar is gonna go to the scan converter, okay, because it needs that information to calculate exactly what time that pulse came back. Okay, so if we have the go time and then we have the receive time, we have the depth, right?
Yeah,
Okay, like in the go return time,
yeah.
the 13 microsecond rule.
Mhm.
Okay, so if we know the time, we know the depth, and we know where to put that dot on the machine, okay? So that's why there's information straight from the pulsar to the scan converter.
Yeah.
Okay? Who can give me an example of something that's analog?
Clock.
Clock. Like, is that the clock?
Yes.
Yes.
It's not-
Okay, that's analog. Okay, so what does that mean?
It's, yeah, it's like not digital.
Okay, so you have to tell the time, and how does this function?
The big one, the little bit.
Well, how?
A battery.
The big hand tells us the hours, the little hand tells us the minutes.
But what moves the hand, or how are those?
Oh, the gears in the back.
A motor.
Yes,
Battery?
mechanically.
Oh my god.
Mechanically.
Mechanically, right? Okay, so there's an actual functioning moving part that's moving the hands, right? Okay, so that's a mechanical or analog clock, right?
Yes.
So what type of transducer does that as well? The
Single L.
mechanical transducer, right? Okay, where it actually moves a crystal so that way it will focus, right?
Seamless, yeah.
Okay?
No.
No.
You're not seeing what? What are you talking about?
Stop just like saying random things out loud.
Oh, seamless are mechanical also, right?
No,
No.
No?
no, they're electronically focused.
said, oh. He said, what?
Isn't that true? Aren't you the same?
Yes.
Yes.
Oh, man.
Embarrassing.
You're making us look bad.
Yeah, it makes me be worried about that. All right, now, what's an example of digital?
The digital clock,
Such as what?
the ones that just let it turn.
Apple
Well,
Watch.
that's in the time, right?
Apple
Your
Watch.
phone, your phone.
Okay, your phone? Okay, so what does the digital do?
Like
It
it-
interprets the information for you, right?
Mhm.
Whereas the analog, you would have to interpret the information yourself. The big hand is in between the 11 and 12, oh, sorry, the small hand is between the 11 and 12, and the big hand, I can't see it, is at the, in between
3 and 4?
three and four, right? So we know that it's 11, what, 17?
16.
16? Okay, it's 11, 16. Where with digital, I could just look at it and say, it's 11, 16.
Mhm.
Okay, so which one is better?
Digital.
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 Because
Okay,
more accurate.
why, more accurate and what?
Okay,
Faster. Yes. Okay, more accurate and faster is what we want from our ultrasound machines, right? Because that makes our image look better. Yeah? Okay. So what type of scan converter do you think we use in today's machines?
Digital.
Digital. Everything is digital. And how is digitally manipulated? Electronically. Yes, very good. Analog?
Mechanical.
Mechanically. Okay, is everybody good? What does the scan converter do?
Converts
Stores information.
the spokes to.
Stores information first, and then it converts it.
Or can we say like it's red, or do we?
I would say convert. Just, just keep that for right now. Okay, so it converts it from what to what?
Spoke into a
Spoke into
video format?
video format, yes. Okay, so analog numbers. Okay, so analog numbers are real world numbers. They have a continuous range of values. Okay, so like pi, everybody knows the number pi, right? 3.4, and then goes for an infinite amount, it feels like. Okay, so those are analog numbers, okay? They have continuous numbers, like 1/3 in decimal is one, or it's 0.3333333, right? Okay, so analog converters had superior spatial resolution, okay? What does it mean by spatial resolution? What are we talking about when we talk about spatial resolution?
Time.
No.
Axolotl.
Axiolateral and?
Temporal?
No.
Elevational?
There's three resolutions that are relative to spatial.
Elevational?
Elevational, yes, okay, because they occupy space, right? Lateral, axial, and elevational. Or ale. Axial, lateral, elevational, ale, right? Okay, ale. Or ale. Okay, fine, whatever you want. Okay, but there were limitations. Okay, we have image fade, image flicker, instability, and deterioration. Okay, are those conducive to diagnostic images? No, they're not. Okay, we may have superior spatial resolution, but everything else would deteriorate. Okay, and it used these types of converters. Okay, does anybody know what a cathode ray tube is? CRT? No? This is how the old school TVs used to function. That's why they had those big things in the back of the screen.
Can't
Okay,
relate.
Light bulbs.
Yeah, those were the big light bulbs, okay? So the CRTs. So it would convert electronic into video in this huge tube. And then this information would be represented as a pixel on the screen. Okay, now it's digital, so it does it with a computer chip. Okay, so that's why we're able to have those flat screens. Have you guys seen those screens that you can actually like fold or roll up? It's crazy. Okay, now we have digital numbers. Okay, so digital numbers are associated with computer devices. Okay, they are very discrete. Okay, which means they only have that set value. There's no 0.0000. Okay, digital scan converters use computer technology to convert images into numbers in a process called digitizing. Okay, when you think of digits, what do you think?
Numbers.
Numbers. Okay, so the scan converter uses computer technology to convert images into numbers. Okay, into zeros and ones. Do you guys know what binary means? Two. Okay, so binary means just two numbers. Okay, like computer code is binary, zeros and ones.
The matrix.
A matrix, that's right. Okay, so the image is stored into the computer memory as a series of zeros and ones. Okay, so what happened here? Okay, so we sent the pulse out. The pulse came back to us, went back into the transducer, went to the scan converter, was transferred from spoke information, which is just the mechanical information, or sorry, the electronic information. So it was turned from spoke to video, right? Okay, now when we press freeze on the machine, what happens then?
It
captures
stops converting.
That,
It captures it, okay? So it's taking that display information and it's turning it into digital numbers, into binary numbers, ones and zeros for storage. Okay, because it's easier for the machine to store those numbers, because it's just two numbers that it has to work with. Okay, so the numerical representation of the image is processed and then retranslated into an image displayed on a monitor. Okay, so does that make sense? It doesn't make sense, right? It's a long process. Okay, so we'll try to map the process, right? Okay, so we have our transducer. Okay, so what happens first?
It stores the video.
No. What happens before?
You plug it in.
The pulsar,
Okay,
the
so
pulsar
turn it
sends
on.
a signal.
It sends a pulse, right? Okay, so this pulse travels, okay? And then what happens?
Reflex.
It reflects.
Surface.
It reflects, right?
Mhm.
Okay, now, what happens here?
It's,
It gets sent back.
it's stored in the machine.
Okay, so scan converter, right?
Mhm.
Okay, so the scan converter, it goes from smoke to
Video.
video information, right? Okay, so when we talk about video, what are we talking about? We're talking about information that can be displayable, right? Okay, but can it go straight from the scan converter to the screen? No. Okay, where does it go to?
To the digital links.
To the digital converter,
Uh-huh.
digital scan converter, okay? So is the scan converter the same thing? So is the digital scan converter the same thing as a scan converter?
No. Maybe.
Yes. Okay, this is the same thing, okay, but we have analog and we have digital, okay? So what happens in the digital scan converter? Okay, so it converts this information, the video information, and turns it into numbers, okay? So from here, it is digitized, okay? It's digitized, which means it's zeros and ones, or binary numbers, right? Okay. Then, from it being digitized, what happens?
Then the image is displayed.
Then the image is displayed. Where the digital scan converter converts it from digitized to video display, or to display, okay? It is retranslated into an image displayed on the monitor. Okay, so right here, we should put retranslated. Retranslated to video, and then the image is displayed. Okay, so that's the process that we're at right now. Okay, so the advantages of digital scan converters are uniformity, stability, durability, speed, and accuracy. So if we have better speed and accuracy, what do we have?
Resolution.
Better resolution, right? Okay, we have better resolution. So which one is better, analog or digital?
Digital.
Digital, yes. Okay. No, okay, I won't get into, okay, so let's continue on. Okay, pixels, you guys know what pixels are?
Yes.
What are they?
Those little blocks that
Makes
go
the
over
image,
there.
more pixels makes the image more clear.
Okay, yeah, okay, so pixels are a unit of information, right? So we can see here that this matrix has 10 by 10 pixels, okay? So what does this look like?
Blurry.
It's blurry, right?
Samsung.
It looks blurry, right?
Yeah.
Okay, now this one has a matrix of 30 by 30, which this image looks like a circle, like it should. Which one has better resolution?
The right one.
3 times.
The 30, right? Okay, so the pixel is the smallest. I guess I should move this on. A pixel is the smallest building block of digital images, okay? The picture density is the number of picture elements per inch. Okay, so do we want more pixels per inch or less pixels?
More.
More, okay, having more pixels per square inch means that our spatial resolution is improved. And what is relative to spatial resolution?
Elevation. Maximum
Axial,
level.
lateral, and elevation.
Axial, lateral, and elevation, right? Yes?
Yes.
Okay, so with low pixel density, we have fewer pixels per inch, we have larger pixels, and our detail is less image, which means that we have a lower spatial resolution, or a degraded spatial resolution. If we have a high pixel density, we have many pixels per inch, smaller pixels, more detailed images, we have a higher spatial resolution.
So in ultrasound, we don't ever want low pixel, right?
No, okay,
Never
so what's relative to the pixels? Or, so, can we manipulate the pixels?
Yes.
No.
The machine,
More machine.
No, okay, so what determines our pixels?
The pulse ratio.
No.
The digitizing?
No.
Digitizing? I
the
don't know.
GPU of the machine,
What?
GPU, like the computer, right?
No. Just the
The
screen
wattage?
itself, the screen itself.
Oh.
Okay, so the screen, when you buy a TV, it comes with a screen, right?
Yeah.
Okay? That, we can't manipulate anything on the screen anymore, right? Okay, so that Fuji, what type of matrix do you think it has?
Bad.
Low.
A low density, right? A low pixel density matrix, right? Because the images look really blurry, right? They look fuzzy. It makes everybody's liver look heterogeneous. Okay, but what about the migrate? What pixel density do you think it has?
Really nice.
High pixel density, okay? But that's the way the screen is, okay? The screen has its set pixel density already. We cannot manipulate it.
Okay.
Okay, we cannot manipulate the pixel density. Okay, so we want higher, pixel density improves what resolution? Spatial resolution. And what makes up spatial resolution? Axial, lateral, and elevation. Okay, bits. Does everybody know what a bit is? What about a byte?
Memory?
By the way, same bit.
Okay, so A bit is not the past tense of byte. Okay?
It's
So-
similar to a pixel, right?
So it's the information that the pixel uses. Okay, so the bit is the smallest amount of computer memory, okay? A bit is bistable, having either a value of 0 or 1, okay? So a bit is just computer information. Okay, if we put a group of bits together, then we get a byte. A byte is a group of 8 bits of computer memory. A word of computer memory consists of 2 bytes, or 16 bits. Okay, so a bit is what? A piece of computer information, right? A piece of information. 8 bits equals a byte. 1 word equals 2 bytes. 1 word equals 16 bits. No?
Well, I guess, but that's not.
Okay, just let that kind of like steep in your head for a bit, okay? Now, each pixel's shade of gray is determined by the cluster of bits assigned to it. Okay? With the increased number of bits per pixel, more shades of gray appear on the image. The more shades of gray improve contrast resolution. Okay, when we talk about contrast resolution, what are we talking about?
Different shades of gray.
The different shades of gray. And what gives different shades of gray?
Compression.
How do we see different shades of gray on the ultrasound? What makes the different shades of gray?
Black and
The different type of tissues.
The different types of tissues, okay? So if we have a better contrast resolution, we can determine the different types of tissues. Okay, so we could say the more bits per pixel, the better improved contrast resolution, because we have more shades of gray. Okay, so we want more bits per pixel. Does that make sense? Okay, if we have fewer bits per pixel, we have a degraded contrast resolution, fewer shades of gray. Okay, so what do we want on our images? We want a high resolution. We want a high pixel density with more bits per pixel. Okay, that's what we want. Okay, so what gets improved with a higher pixel density? Spatial resolution. And what gets improved if we have more bits per pixel? Contrast resolution. Okay, so it improves the spatial resolution and the contrast resolution. Okay, having more pixels and having more bytes or bits per pixel. Does that make sense?
Yes.
Okay, so what makes up a byte?
Eight bytes.
Oh.
8 bits. 8 bits equals a byte. Okay, what makes up a word?
2 bytes.
2 bytes or 16 bits, right? Because 8 times 2 equals 16, right? Okay, now what determines the shades of gray? The bits, okay? The bits per pixel. The bits per pixel. So the more bits per pixel, the more shades of gray. Does everybody understand that?
And bits is like directly related to pixel because it's one-on-one ratio, right?
No. No. A pixel can have a lot of bits or a few bits. Okay? They're not directly related. Did you get lost, Victor?
No, I just thought that it was like directly related.
No. Not quite. Because we could have a high pixel density, but we have a low number of bits, and it could make our image look bad. Or we could have low pixel density that has a high number of bits, and it'll make our image look better because we have more shades of gray.
Okay.
Okay. All right. This will be kind of confusing, okay? So to determine the number of gray shades that can be represented by a cluster of bits, multiply the number two by itself, the same number that there are bits. Okay. So, if we have 3 bits, we have 2 to the third shades of gray. It's always gonna be 2. So 2 is gonna be the set number, and the exponent is gonna be the number of bits. Does everybody understand that?
Yes, the number 2, what does it like represent?
2?
That's it?
That's it.
Okay.
And the exponent is the number of bits, right?
Yes. Okay, so 2 is gonna be the root, that's gonna be the
Okay.
constant. Okay, 2 is gonna be the constant. I don't know why it's 2, it just is. Okay? The exponent is gonna be the number of bits. Okay? So if we have 4 bits, how many shades of gray do we have? 16. Okay? Because it's 2 times 2 times 2 times 2, which is 16. Okay? So that's why the more bits we have, the more shades of gray we have to work. Okay, so if we have a byte of information, and that byte has 3 bits, how many total number shades of gray do we have?
8.
Wait, how many bits did you say?
Huh?
How many bits did you say?
Say that again.
Yeah.
Okay, we have 2 bytes.
So 16 bits.
Oh, 2 to the power of 16. I don't know.
Okay, no, wait. Okay, go on. We have 2 bytes,
16 bits.
and each of those, or we have. I'm just gonna confuse you guys. Okay, so let's say that we have a word of information.
Okay.
Okay,
The 2 bytes. 2 bytes?
okay, at each bit, or there's 3 bits.
Per
Okay,
byte?
yeah.
Confused.
Okay, never mind. Okay, let's just go, the more bits per pixel, the more shades of gray, the better the contrast resolution, right? Okay, the higher the pixel density, the better the spatial resolution. Okay, let's just stick to that. Okay, and we know that the number of bits
Is the
gives us
exponent.
the number of shades, right? Okay, so if we have 3 bits of information, we have 8 shades of gray.
And a byte will always be 8 bits, right?
Huh?
A byte is always going to be 8 bits?
Yes.
Okay.
And the word is 2 bits,
Mm-hmm.
16 bits.
16 bits, which means how many shades of gray? Right, 2 to the 16.
That's a lot.
So the
That's a lot.
shades of gray, the number there, it's always like 2, 4, 8, 16.
Yes.
2,
Okay, so 2 is always gonna be
yes.
no, not the exponent, it's gonna be the base. Okay, it's gonna be the whole number. The number of bits is going to be the exponent.
Oh, okay.
So
Yeah.
does this mean we won't be able to see like after 5 or after 4? So we can only see 20 shades?
Yeah, pretty much.
Oh, okay.
Okay, but the computer still uses all that information.
Mhm.
But what makes sure that it's within the visible range or human eye?
Compression.
Compression. Okay, compression keeps it within that range where we can detect it. Okay? So, when it comes to, sorry. You used to see this, right?
Yes.
Okay, so pixels are relative to the image element, image detail, and spatial resolution. Okay, that's pixels. Okay, bits is relative to the computer memory, the shades of gray, and the contrast resolution. Does that make sense? Okay, so if I tell you what's relative to spatial resolution, you would say pixels. What's relative to contrast resolution?
Bits.
Bits. And what do we want when it comes to bids?
More,
More sheets.
more,
More-
more bids,
More bids
or more
Per
sheets
per
of green.
pixel, per pixel, right? More bits per pixel, which makes our contrast resolution improve. Okay. If we want better spatial resolution, what do we want?
More pixels.
More pixels per inch, per square inch. Remember that it's square inch, okay? Because it's 10 by 10, 20 by 20, 30 by 30, it's gonna be square inch. Okay. So we have analog to digital image information. Okay, translating information from analog back to digital and back to analog is a 5-step process. Okay, so first it goes to the analog to digital converter. Okay, so you guys remember when we got that information from the transducer, we had to what?
Store it.
We have to store it, and then when it gets stored, what does it do?
Process.
It gets digitized, right? Okay, so analog information is digitized. Okay, so the analog to digital converter, okay, it is stored as digital memory. And then that digital memory is then converted back into what? Video.
Oh, yeah.
Video, right? And then it is displayed.
Yes.
Okay, and that all happens in the converter. Okay, so it happens in a 5-step process which follows. Okay, so the signals created by the transducer during reception, which means the echoes, right? Reception or receiving, are converted from analog to digital, formed by the analog to digital converter. Okay, the digital information is stored in the scan converter. Then, the digital information is still being processed by the ultrasound system. These signals are then turned into analog in order to be displayed on an analog display. This is done by the digital to analog converter. The signal, now in analog form, is presented on the analog video display. Okay, so he's just saying, it's pretty much elaborating on the process that we talked about in the picture that we drew, right? Okay, so that's pretty much, it's breaking it down into those 5 steps. Okay, analog to digital, storage, digital to analog, display. Very simple. Even though it sounds complicated, it's not that complicated, okay? Is there any questions? No questions?
This slide was just basically elaborating on that.
Yes. That's all it is. Is there any questions?
No.
No? Okay. That's gonna be it for class today, because I have to speak to the other